Hello, hello. Great to see everyone. Thank you for joining us, whether you're live or watching this after the fact. It's exciting to get the opportunity to start a new topic today. So we're going to be talking about strings. How's everybody doing? Here's my question for today. How is everybody feeling? How are you feeling about what we've been doing, where we are? We'll use our math scale of 0 to 10. Since we love base 10. How are we feeling about the material so far? Okay. Was a 10 still a 10? I guess you might not be here if you weren't reasonably high, which is good on that scale. I think I mean also in terms of, well, yeah, math is always a 10. Math should be a 10. I like seeing that, Robert. But just in terms of your comfort level with what we've been doing. I mean, I know we've had some long streams on here, and some of them, especially the one that we're about to do, is not going to be as long as what we've done up till now, because we kind of need to jump in the deep end a little bit, right? And just get comfortable with this. And that first chapter is actually really probably the longest one because we have so much to get comfortable with. And as I said a few times, it's probably the hardest because there's so much foundational material. If you've seen all this before, then obviously it might just be in a new language for you, or you've already had some experience with Python. So some of it might be a repeat, but it's by far the moment where the most people eject. So if you feel comfort now, I'll just say, I think you have every ability to carry this out and do not just this course, but do much more advanced stuff in computing, if that's what you want to do. So I'm excited to see other people are excited. Even if you're a 5, I don't mind that either. As a reminder, we have exercises that can accompany the first chapter of material. So if you have any questions with that, this is what office hours are for. This is why we have a Discord. You can interact with each other. We're going to try to roll out some additional things to allow you to work together on these. Looked like there were some questions about like deadlines. And one of the things that I think I'm trying to do with the course as a whole is create something that doesn't necessarily have hard deadlines. We've got a cohort of people who are watching this live and trying to follow the material as we roll it out, which is great. It's also going to live somewhere for a period of time. So if you find that, you want to come back to this another time, or you want to come back to part 2 another time, or whatever pace you want to go at, that's completely fine. I will say, I thought about establishing deadlines. It's not something I chose to do because I want the course to be completable at whatever pace you're at. But I will say the best way by far is to show up, code along, be on the schedule that we're on, and stay on the treadmill. I talked about the treadmill at the start of the first stream that we had, which is that a lot of what I find that people have challenges with programming is that it's easy to kind of step off the treadmill and you miss a week's worth of material. And some of that is very important for, because everything is like this big staircase that builds. And so as long as you keep going, you're in good shape. So I'd just say, if you're ever in doubt, come join us. Don't miss out on a stream. It's better to just keep going than it is to step off. But we don't have hard and fast deadlines. So if you want to not complete an entire collection of practice exercises and come back to it later, that's fine by me. I want you to complete this in whatever the way is that works best for you. So we're about to get started. The one thing I would say too is, it's just my funny story from today, is we were all, because it continues to get colder and colder and snowier, regardless of how many remarks I make about it. But we wound up having so much today that we had fully remote classes. And so I'm on a text thread with some other professors. And one of the things they were saying was, can you believe this, how awful it was? It's just like going back to 2020. We were completely remote. I had to figure out how to do everything again. I just hate teaching online. And I was thinking, it's probably my favorite teaching day of the year. I just get to stay online and interact with my students in the chat, and all this, so I was kind of in my element. But that having been said, 2020 I really enjoyed. Is there anybody else who feel like they thrived in 2020? Or is that just me? All right, Samuel, I don't know if I believe you, but I like that you thrived. Even if you're just saying it for my account. I appreciate it. All right. Yeah, you didn't have to go into the office. If there's any reason you didn't like going into the office, yeah. It was a wonderful time. It was the heyday for introverts. It truly was. And as an introvert myself, for whatever reason, I'm just comfortable sitting in my house talking to a screen, and I could just do that all day. It was wonderful. And there were a lot of meetings, wink, wink, that you could kind of be in, but maybe not be paying the most attention. That's also wonderful. But let's get started though. So enough overview of the class. As always, if you're not in our Discord, this is an opportunity to have some community and continue the great community that we have in the chat on over there. And make sure to like and subscribe on YouTube. We also have subscription for office hours. We'll be having some bonus sessions at some point too. So join us there for that. In the meantime, today will be hopefully a little bit shorter of a stream than what we've been doing. And what's nice about it is a lot of times, even though this is a treadmill, we're going to keep going forward on the treadmill. And I think sometimes there are some opportunities for us to kind of maybe not go backward, but slow down a bit. And so what we're going to do today is really going to build on a lot of the stuff that we did towards the end of the previous chapter. It's not going to necessarily be easier, but there's not going to be a lot that's tremendously new. And so it's an opportunity for us to just cover some basics and a couple areas that we need to. We're going to start off with the basics of strings today. This is all based off of our chapter that we have on Programming for Lovers on the website homepage. So check out that reading. That reading is always really good to kind of prepare you for what we're doing here so that it'll be clear where we're going. We're going to do the basics of strings today, but the whole idea is that we want to look for hidden messages in genomes and look for some algorithms that are actually practical that we could apply to some basic bacterial genome analysis. So check out our reading on our course website. And other than that, I think we're ready to get started. So we're going to work with strings. And to get started, let's create a strings folder in our Python src source code directory. And even though we're comfortable with this, we're going to create any folder, any file called .py. So I'm going to have a main.py in my strings directory. And we're going to need, of course, our def main. And I'm going to add a simple print statement that just says strings. And then we need our special two lines that say, if we call python3 main.py and execute this code, then we need to run what's present in main. So I'm going to say, if it's the case that our special variable called _name_ is equal to this string, which is _main_, then we're going to call the function main. All right. And we want to work with strings, and we've already worked with strings before. So I've introduced them very briefly when we talked about variables. But strings are variables just like integers or decimals or Boolean variables, anything like that. The string itself then needs to have a name. So I could have one string and its value associated with it would be, let's say, hi. The other thing is that the value of a string can be enclosed in single quotes or it can be enclosed in double quotes. So you've seen strings before when we pass in anything to a print statement. A lot of times we'll pass in a message, and that message can be represented by the string that we want printed to the console. So I'll say S is going to be the string hi. We also can use double quotes, as I said, which is what we're going to predominantly use. And let's say that second string is going to be called lovers. Just like with integers or decimals, we have some, not all, but we do have some like arithmetic operations around strings. The main one being what's called string concatenation. So concatenation is what we think of when we glue together strings. And so if I use the notation S plus T, the indication here is that I take whatever the symbols are in S at that point in time. I take whatever the symbols that are in T at that point in time, and I just glue them together where S comes first and then T comes. And one of the things I could do is I could say, well, let's set a new variable u equal to the result of that, just to get comfortable with operations like this. So this operation works in the same way that it would for an integer. We say, what are the values currently of S and T? And I'm going to add those together. In this case, I'm going to concatenate them together. And then I'm going to set that value equal to, or set a variable u equal to that value. Once I've done this, I could say print u. And I'll go ahead and show you what results. So we can pull up a terminal. We know I'm in my Python directory. And I can say, let's navigate into the source code directory, and then let's navigate into strings. And we can run the code that we have just with Python 3 if you're on a Mac, or Python if you're on a Windows machine. I'm on a Mac, so I'm going to say Python 3. And then we can run main.py, since that's our file. And what you'll see is BC says, oh, I forgot the space. And that's not really that I forgot the space. It's that I'm just showing you that when you perform this concatenation, it doesn't give you any extra space. If you wanted space, well, you could add it in a way like this. So there's nothing wrong with repeated concatenation in the same way that there's nothing wrong with nesting multiple arithmetic operations. So if I save that and then I ran it again, you'll see the space get printed. In the meantime, I'm just doing that to show you. I'll leave it as S plus T for now. You might also wonder, is there like a multiplication? This is actually, I think, a pretty neat thing about Python. Now, I'm not 100% sure why you would ever want to do this, but what we could do is to say print S times 3. And I should say multiplication with strings is just like it is with arithmetic. It's repeated addition. So in the case of strings, it's repeated concatenation. It's kind of a nice feature, one I thought I would show you. Not one that's tremendously useful, I don't think, but in this case we could print the string hi copied 3 times. So this would just say hi, hi, hi. Now, the next question might be, what is a string, right? In the grand scheme of things, well, we think of a string as this collection of contiguous symbols, but is there another way that we can think about it? And the way that I want you to think about strings is that strings are kinda tuples of symbols. So we've worked with tuples before, and what we've seen before is that in what many languages would call arrays, which are collections of variables that are grouped together into one place, Python has both lists and tuples to represent them. So we're comfortable with this before. And so we think of a string then as a tuple where all of the elements, each element of that is in turn a string that contains one single symbol. And if that's true, then what that means is we can work with strings in the same way that we worked with tuples. So for example, I could access individual elements of a string. So I could say, for example, I don't know if I'm interested in the first symbol of u is, I could say u of 0. Similarly, we know automatically then how to access for an arbitrary string. We know how to go in and grab the final symbol. So I could say the final symbol of u is. And in this particular case, well, we could count out and say exactly how many elements are there in this string, but I always know that the elements of a tuple are indexed from 0 up to the length of the tuple, but we want to be careful because if we start counting at 0, then we're not going to end at the length of u, we're going to end at the length of u minus 1. Okay, and so we know that the first symbol of u is h, and the last one is s. So when I save this and I run, we should see, let me write in complete sentences, that the first symbol of u is h and the final symbol of u is s. Everything's working well there. We can also even check equality. So you could even do something like, if it's the case that t of 2 is equal to, and here we check it as a string. So I said it's almost like each symbol corresponds to its own string. And if that's the case, here we get to use an if statement, like what we're getting comfortable with. Then I would print, I don't know, the symbol at position 2 of t is v. And the question is that true? Well, how did I define t? I said it was lovers here, and we remember L is at position 0, O is at index 1, and V is at index 2. So when I save this and I run it, we will see indeed that this gets printed because t of 2 is equal to V. A quick note, just in case you haven't worked a lot with strings before, is that the symbols here are case sensitive. So if I change this to a capital V and then I run it again, you're not going to see this print statement get executed, and that's because the case matters. So I'll keep this as a lowercase just so you'll see that this print statement gets executed. If I'm telling you that strings are tuples, and I'll give you a hint that I've seen it a little bit in the chat already, which is good. There's a review. There's something that we know about tuples. So what did we know about tuples? There's a fancy way that I described tuples when we first looked at tuples and lists. What's the fancy word that I use? Good. We got a good your memories are better than mine. All right. So, but I said strings are tuples. So strings, like tuples, are immutable. And here's where we know enough about what it means for something to be immutable to now say, okay, well, what is that? What are the consequences of something being immutable? And we remember back, well, what did it mean for a tuple to be immutable? It meant that you can't change individual elements. So this fancy sentence now gives me this understanding that if I tried to go in and say, I didn't mean to say hi lovers, I meant to say hi losers. So let's do, what a mean thing for me to do. So say I tried to set, I don't know, u of t equal to the string s. Or let's see, t of 2. It won't even let me do it. T of 2 is equal to s. Okay, and I saved that, and I ran it. Well, this is not allowed. Okay, so I can't, once I've declared a string, I can't change individual letters. That's not good. So the string is set. Now, of course, you can change the whole string. So I can, like you can change an entire tuple all at once. I can change the entire string. So I could set s equal to yo. And I'll just show you, I'll print s. And that'll work. So we see that yo gets printed. Now, of course, it doesn't change anything back here because this is the current value of s. So this is after we've already set u equal to s plus t. So u is still going to be hi lovers, but s now changes to be equal to yo. One more thing with arithmetic, though, which is you might be wondering, okay, well, if I can do concatenation, does that mean I get things like the plus equal shortcut? So remember, I might want to do something like s equals s plus let's give it another yo. And I'm going to add a dash there because I want to be precise. You'll see why here in a second. This is fine too, because a statement like this is not changing an individual element. It's saying, what's the current value of S? Concatenate this additional string with it and update S to be that value. So I could do this as much as I like. I could do S equals S plus, and I'm going to do space and ma. And then we're going to say, well, we can use the plus equal shortcut too. So I don't need to write it this way. If I had integer variables or something like that, I wouldn't write it this way. I would probably get comfortable just doing plus equals. And the same thing down here, I would say S plus equals. So at each stage, we're just appending more symbols to the string that we already have. And then I could save that and run it. And then we could say, what's this going to produce? It's going to produce yo-yo ma, the famed cellist. Now, this is all well and good, but the point is, because we've learned about tuples and lists, and we can kind of use everything within that framework already, strings now should be pretty comfortable. And it means that even with this short introduction to strings, we could write a function to do something realistic, like reasonable with a string. And so one of the things that I might do, which is a hallmark of computational biology, is I have a string of DNA characters representing a gene or a genome or a chromosome or whatever, and I want to look at what's on the opposing strand, and so I need to perform this reverse complement operation. So I might want to write a function called reverse complement, and I'm going to take a string in this particular case. It needs to be a string of ACs, Gs, and Ts. So I'm going to call my string, let's just go ahead and call it DNA. The type here, you want to type string. That's close. You see it's underlined in yellow. I'm getting a syntax warning. The type here is technically just str. So that's where we saw it had ints or floats or bools in Python. The string type is called str. And we can have type hints with str as well. So we're going to maintain our type hints. We're still going to make sure that, oh no, that we always generate a doc string. I've got some tool there that's automatically filling in a doc string for me. But we're going to generate a doc string, and I'm going to say what it is that this function does. So this function produces the reverse complement of a DNA string. So this is A's, C, G, and T, symbols only, meaning the string corresponding to a complementary strand. Okay, so if you know a little biology, you know that DNA is double-stranded, but the strands run in opposing directions. So you have that A binds with T and G with C, but then the strings get read in reverse directions as well. So if you know one strand, you get the opposing strand for free. So for example, the reverse complement of a string like AGTC is, well, you look at it in reverse order, but then you also do the base pairing complementarity. So you would start at the end, which is a C, and you would say G is the first symbol, since that's the complementary nucleotide of C. The complementary nucleotide of T is A. Then we're going backwards. The complementary nucleotide of G is C. And then the complement of A is T. So here I would say parameters are going to be a string, and that's the only input that I take, and the output is going to be a string, which is the reverse complement of the input string. Now, here's where I'm going to ask you, how is it that we might write a function like this? Knowing what we know now, does anyone have a way that, and this, I'll give you a hint, is a little bit of a refresher from the reading, if you've done the reading. What's a way that we can write my function as simply as possible? What's our idea for how we actually implement this reverse complement function? So Yasmin says we could read the list from end to beginning. Okay, so we could do some kind of ranging. I like this idea. We could start at the end of the string, and then we could work our way backwards. And as we go, so that's sort of how I was thinking about the problem here. I could go backwards and say, start at the end. What's its complementary nucleotide? Its base pair is G, T's is A, G's is C, A's is T. That'll work for sure. We've got another good idea, though, which I like, which I'm going to show you, which is there are two tasks here. One is reversing the string. The other one is taking the complementary nucleotides of each symbol in a string. And so one of the things we could say is to say, update DNA to be what happens when I write another function that's just called complement. So this function that's just called complement is not going to reverse the string, but it is going to take the complementary nucleotides. So the complement of A, G, T, C is just, well, what base pairs with A, it's a T. What base pairs with G, it's a C. Then A, and then G. Once I perform that complementarity, you'll notice, well, this is the same string as this, it's just reversed. So then I could say DNA equals reverse of DNA. So we have another string, another function that just reverses the symbols in a string. And once we perform these two independent actions, we can return DNA. Okay? And that's one way of writing this. And that provides a way that's much shorter than thinking about the process of ranging through this and going backwards and then doing the complement. So you have two very separate tasks here. Each one is easier than the other one. I'm going to make another remark about this because as we go through the class, this is one of the most important things I'm trying to convey about how good code works, which is that rather than try to solve a problem, a lot of times we're striving to be lazy and just kick the can and delegate. And in this particular case, we've delegated to two very different tasks that are also easier than what it is that I'm trying to solve. We'll come back and say more about this. For now, I'll say, in practice, I wouldn't write it in this way where I keep updating DNA. I'm going to keep these because I like having my comments at the end. All I would do would be to say I'm going to return the result of reversing the string after I complement it. And so we have a one-line function where, yes, I have to write two more functions, sure, but I have a one-line function that's going to satisfy this for me. Now, I need to write each of these other functions, and I'm going to start, we could do them in either order. I could start them with complement. For now, I would ask you, what happens if I switch the order? Do you think that gives me the same end result? So think about what's going on here. In this case, we would reverse the string first, and then we're going to take the complementary nucleotide at each position. In that particular case, would you get a correct result in the end? Let me know yes or no in the chat based off of what you think. All right, a lot of yeses, some no's. Let's think about this. So in this particular case, if I complemented it second, so if I reversed it first, well, we would reverse this first and we would say CTGA. After I reverse it, I've got CTGA. And then when I've got CTGA, I'd say, what's the complement of C? It's G. What's the complement of T? It's A. What's the complement of G? It's C. What's the complement of A? It's T. So reversing the string first and then complementing it would give you the same result. Doesn't matter. In the meantime, I wrote it this other way because I like the idea that the reverse complement is reversing the complementary string. And now we can write these. So let's write a function called complement. And this still needs to take a DNA string. We're going to tell it what the type hints are. And I'm also going to return a string. And do not want to generate the doc string automatically. That's just going to do it for me. Okay. Well, I'll delete that. Okay. The complement function is going to do this simpler task of just taking the string where we complement each nucleotide. It's not a biologically useful function, I don't think, but we're going to say the string performs the complementary. Let's think about how I should specify my top level function here. I'm going to say finds the complementary strand of a given DNA string without reversing it. Let's put it that way. And we could say the parameters here are going to be, well, DNA is a string, and the return is going to be string, which is the string whose ith symbol is the complementary nucleotide of the ith symbol of the input string. So we know A binds with T and C binds with G and vice versa. Okay. And now we know how to write a function like this, which is we want to range over the string. So we want to range over the string and take the complement at each position. I know how to range over things. In particular, I'm interested in the current position as well as what that value is. So here's an opportunity for me to show you or remind you that if I care about ranging over the indices and the values of a tuple, a list, a string, whatever, I can have our for keyword, and then the variable I want to use as the index, and then the value, and then I'm going to say in enumerate whatever it is that we're ranging over. So it's a string, which is kind of like a tuple. So this will range over all of the simultaneously. I will range from 0 up to the length of DNA minus 1, and symbol is going to give me the current symbol at each stage. All right. So I will test to say what's the current symbol in my string. And I'm calling that symbol. So I could say if symbol is equal to A, then I'm going to do something, and maybe I'm going to say let's set DNA of I is equal to the symbol T. And here's a great opportunity for us to use if, else if, because we have multiple cases. So if the symbol is A, we're going to do that. If symbol is equal to C, well, I'm going to set the symbol that I care about equal to G. Else if the symbol is equal to G, I'm going to set DNA of I equal to C. And then else if the symbol is equal to T, we're going to set DNA of I equal to A. And we probably should have an else. One of the things that we have not done is we haven't tested we haven't checked the input string in any way. So with integers, we would often need to check and make sure that those integers are within allowable ranges. And so we don't have this equivalent of that here, but what we do have is maybe we want to ensure that somebody's giving us a DNA string, because if somebody gives me the letter Q, I don't really know what to do with it. So what we could do is we could say in those particular cases, let's just raise a value error and say error symbol in the string is not a DNA nucleotide. All right. And that's our function. Of course, I tricked you, which I like doing. It's one of my favorite things. I didn't trick everyone. So somebody says there's something we know about strings, well, for one, I've not actually written a function. Okay, return DNA. All right, now I've written a function. But there's something that we know, we already have learned about strings. We know one critical word about them, and that's that they're immutable. So this is not going to work. And I wanted to point out, this is kind of like how we might think about the question. So there's nothing wrong with writing code that's wrong with respect to a particular language, as long as we understand why that's the case, and as long as we understand how to work around it. So the way to work around it in this particular case is to say, I know that strings are immutable. I can't quite do this. I'll never be able to set an individual symbol of anything in a string. But what I can do is say DNA2 and start it off as an empty string. And then I'm going to range over the original string DNA. And Claudio says, why not just concatenate to it? So instead of trying to set individual values, that's exactly what we're going to do. I'm going to keep building up the string. And in this particular case, I actually am never going to need to care about what the current index is. So I'm just going to say for symbol in DNA. Remember, if you range over a tuple or a list, and you just use a for loop like this ranges over the symbols, which is nice. So at a given point in time, I've got a for loop, and this is telling me that this is the current symbol in DNA. So the current symbol in the string, we're going to check. We're going to say, is symbol equal to A? If so, I'm going to concatenate T to the end of it. Is it equal to C? If so, I'm going to concatenate G to the end of it, and so forth. So I'm just changing all of these to plus equals. Here's our opportunity to use the shorthand that we introduced a little while ago. All right. So now at the end, we don't return DNA. That would produce some really bizarre output. We're going to return DNA2. I want to run this, but I also want to use this as an opportunity to say, this was a great review of if and else if statements. I'm also going to show you a little bit tighter of a way of writing this. So a lot of times when you have a lot of cases, writing if, else if, else if, else if, else if becomes somewhat tedious, and this is perfectly fine. Nothing wrong with it at all. But I'm going to show you a little bit of a cleaner way of writing it that a lot of languages have, that Python has introduced more recently within its lifespan. So this is what we're going to introduce is called a switch statement in a lot of languages. In Python, we will use a match statement. Okay, and many of you are saying, oh, well, what about this? Why am I appending the DNA? Okay, I need to append a DNA too. Technically correct, sure. But I'm not going to use an if statement at all. So I'm still going to start DNA2 is equal to an empty string. So it has no symbols. I'm still going to range over DNA. So far, so good. But I can simplify this quite a bit if I say instead of if symbol equals A, I'm going to have a special statement that says match symbol. Okay. And the match statement is called a switch in other languages. The idea is it's based off the notion of like railroad switching. So we might go this way, or there's all these possibilities that we might take. And so but to preserve that analogy in other languages, it's called a switch, but it's called a match in Python. Same idea. So I'll preserve this same sort of structure, but when we write a switch statement, everything is with respect to cases. So when I write match symbol, I'm not matching anything. I'm saying, what is the current value of symbol? In the case that the current value of symbol is A, well, I'll set DNA2 plus equal to T. In the case that it's C, I'll concatenate G to the end of it. In the case that it's G, I'll add a C. In the case that it's T, I'll add an A. And then we're going to need a default case, which is what happens if none of those, so the train's coming off the tracks, I guess. We've tried all of the possibilities that we've specified for the symbol, and we're going to raise a value error. So to do that, if you have a default case, we're going to do case underscore, and then that's where I'm just going to copy in my raise value error. And then at the end of that, we return DNA2. Right. Yeah, so BZ said it's new for you. I think it's new for a lot of people that, yeah, there are these things that Python has added that are really good, that have definitely allayed some of my frustrations with Python. One of them is something like a match statement. The other is type hints. Type hints are relatively recent, and we'll see a lot of things throughout the course that I think are things that are not necessarily like classic Python, but are things that they've added through its lifespan because people were saying there's other things that other languages have that are nice, and if Python's going to try and do everything for everybody, it should probably have these things. So in the meantime, we should probably run this. So I could go into main. I don't have a lot in main currently, and we just had our initial yo-yo mon high-level strings. Let's establish a sample string. So I'm going to say DNA is equal to ACCGAT. Okay, and let's look at the complement of that. So I'm going to print the complement of DNA. And I don't want to save. Already saved. I think I was saving as. So we know what the complement of this is going to be. It's going to be TGGCTA. And that's what we should see. TGGCTA, I hope. So when I save and I run, I see TGGCTA. So our function appears to be working. It's got the appropriate length. I'm not doing something silly like what I was doing before where I was modifying DNA and just adding to the end of it. And our function appears to be good. So let's write the other subroutine. We've written complement. We should write reverse as well. And we know what this function is going to do. So this function should be called reverse. In this particular case, I could imagine it doesn't have to be a DNA string. It could be a function that I could reuse in other contexts. Anytime I want to just flip the order of all the symbols in a string. So I won't call it DNA. I'm just going to call it S. And it's going to return a string. And I want to give this function to you. So I'm going to ask you to say, let's give you the opportunity to write this function, knowing what you know now. I'll go ahead and write the doc string a little bit. So I'll say reverses the symbols in an input string. The parameters here, the parameters are going to be S as a string, and the return is going to be a string. That's the reverse of S. You know enough to do this, so I'm going to leave this to you as an exercise. I believe in you. I'll give you a couple minutes on it, and then we'll come back and discuss. You're welcome to do it in the chat. I don't mind. I think some of the, I'm going to give you about 30 more seconds. You don't have to have a final answer. That's okay. I do think some of the shortcut stuff I see in the chat, I think you're all just trying to trigger me and some of my thoughts about Python. So I'm gonna make some remarks on this. If you have a one-liner, I'm not upset. I'm proud of you. If you're aware that there's a one-line solution to this, but I'm not going to show a one-line solution to it, and that's going to be for a specific reason. But we're going to take the opportunity to solve this here in a second. All right. So how I'm going to write this is I'm going to think about the same way, right? How would a human do this? Well, they would start at the end of the string, and they would think about building out the other string by starting at the end and going backwards. The other way we might do it is to range through the string and build it backwards. So like look at the first symbol and then start trying to put it the other way. But that's going to be hard to do with string concatenation. We can do it that way. It's probably more natural to build up the string starting at the end. So I'm going to start with a blank empty string, and I'm going to call it rev, for short for reverse. And way down here, that's eventually what I'm going to return. Now, it's not tremendously useful, but let's just call n equal to the length of s. So then I could say, what am I doing? I'm ranging over s, and I could have done it this way, but it's nice to just say, let's range over n. Because what I want to do is, I'm ranging over all possibilities. At every point in time, I want to append or concatenate to the end of rev something, right? And part of the reason why I'm not showing you a shorthand, the reason why I'm the reason why I'm not showing you a shorthand way of doing this to do it very quickly is that then that's going to be the sort of thing that you then have to commit to memory and think, oh, well, if you know this shorthand way of writing this function, then you're a genius, right? So I know I don't even need to think about writing a for loop because Python provides some built-in way to do it. But what that's missing is that what I'm asking you to do here is also the type of skill that regardless of how many built-in things your language provides you with, you're eventually going to hit a point where you have to solve problems on your own. And this is the type of problem that if this problem is that we should not be scared of. Let me put it that way, right? If this might be new to you, and that's okay, but an experienced programmer would have just as easy a time writing this function than they would to remember a one-line shorthand. And so if you practice writing code like this, if you haven't done it before, it's going to make you stronger when the time comes that there simply is no shorthand way of writing it. We can't remember how Python does something quickly with some built-in thing. The training wheels are off, and we're on our own, and we're going to have to solve a problem by ourselves. And so for that reason, that's why I don't show you the tricks, because I don't think that the shorthand tricks for something like this make you a very strong programmer at the end of the day. And part of the reason why I say that is because, well, what we need to do here is we need to notice a pattern. And ultimately, we start the course with math, and I say math underlies everything that we do in so much of programming and computer science. And here's an example of what I really mean by that, which is that, well, when I is 0, I need to know exactly what symbol of S I'm grabbing. So when I is 14, I need to have some relationship, and I need to know what is the index of S that I care about. And I could just go over here and write in the comments, and I could say, I have a value of I, and I have an index of S that I care about. And I starts off as 0. So this is going to be the first initial value of I. And then, well, when I is 0, the index of S that I care about, and I used n for a reason, because the index of S is n minus 1. So When I is 0, I'm looking for position n minus 1 of S, and that's the symbol I'm going to grab. When I is 1, I'm looking at the symbol at position n minus 2 because I'm going up by 1, but I'm going one step backward in terms of S. When I is now equal to 2, I'm interested in n minus 3. And so forth. So there's, in general, you'll be at position I. And what we need is a formula and to notice this pattern. So the final element that I is going to have is n minus 1. And then the index of S that we care about in that particular case is 0. So then the question then is, what is it that I care about in terms of the pattern that I notice, right? How is it that all these things are related? In general, is there a general equation for I here, or for the index of S for general I? So when you have an arbitrary value of I, what's the pattern, and what would we say is the index of S? Somebody tell us. What do you think, chat? Inversely correlated? Okay, and when I see inversely correlated, I'm thinking of doing a division. We have n minus I plus 1. Now I put that to the test. When I is equal to 0, is this n minus I plus 1? No, because this is n minus 1. n minus I plus 1 would give us n plus 1. So that's not quite right. You are noticing something, which is that at every point in time, this is going down by 1. So this is n minus 1, this is n minus 1 minus 1, this is n minus 1 minus 2, and now we start to see the pattern. So at this stage in time, it's n minus 1 minus I. Okay, and that holds up all the way down here. This is also n minus 1 minus I is n minus 1, so those things cancel out and you get 0. So this is the type, again, my point about why we do math is that you can't do programming or computer science, even if you have, for some introductory types of problems, you have these built-in things that allow you to do things quickly with shorthand. Eventually, you're going to hit a point where you notice that there is a pattern somewhere. You need to express that pattern in language. And it's like, at the end of the day, that pattern is algebra. Right? So here's another little bit of algebra here that's telling us this is n minus 1 minus I. And we can write it in parentheses like this if we want. That might make things a little bit clearer so you understand this pattern. It doesn't matter. You can even move the minus I into here. However you write the expression, it's all going to be the same. Okay, but this is our function reverse. There is a way of doing this a little bit faster, okay? And it's my minor note on efficiency, because I think there's opportunities to tell you about these sorts of things, which is a lot of times you might write this function and then you're like, oh, this is cool. I can do the reverse complement of a huge 5 million nucleotide long bacterial genome just to do it, right? And test your function. And then you do it and it's like, this function is taking forever. Why is it not any faster? All it's doing is ranging over n symbols. Like, that's not very complex. And so you actually wouldn't write this function, a function like this, in this way in practice. And the reason why is, remember, strings are, what's the fancy word? You only have to know one word in this particular code along, and it's immutable. And every time you do this, this actually is essentially creating a brand new string. So this is saying rev is equal to rev plus this one symbol. And so it is copying those two things together. And because strings are immutable, it can't change individual symbols. It's got to change the entire string. So it then like reallocates all the memory associated with rev. That's not a big deal if this is a short string. If this string has like 5 million letters in it, it becomes a big deal. So this is going to really slow us down. And I'm going to show you a way that we can get around that, because memory, we're going to talk about memory much later in the course, but memory is just as important a consideration as anything else, and it can slow our programs down. So instead of creating an empty string, I'm going to create an empty list. And then I'm going to still do this ranging, except instead of appending or concatenating the string, I'm going to append the symbol that I care about. And the symbol that I care about is what we just had. The symbol of S occurring at position n minus I, or 1 minus I. And then you're like, well, how do I get a string out of this list of characters? A lot of languages will have this. Python has a way of converting this. So I'll say, now we need to convert this list to a string. And we can do that by saying, using the command empty string dot join characters. So that's a built-in function that takes a list of things and it joins them all together. It kind of just glues them together into a string. And this is what's called the separator. So if you wanted some additional space in between characters or some kind of other symbol or collection of symbols, you could put it here. We don't care about that. We just want to glue them all together. And so that's going to mean that we just return empty string dot join of this list of things. And if you don't believe me, go get a big string, try it out for yourself, compare the runtimes of the two approaches, and you'll see that this is much better. To put this all together, I want to make one final point about what we're doing, and we should probably test our function too. So I should probably ensure that when we go to main, we can print the complement of DNA, we can print the reverse of DNA, and that should give us TAGCCA. And what we really care about is this reverse complement function. And that should give us the reverse complement of ACCGAT, which is ATCGGT. And so we can ensure that when we run, we see that the reverse is TAGCCA and the reverse complement is ATCGGT. Everything seems to be in order. My question is, why is this a good thing? What is it that about the way in which we wrote this function? Why was this the right thing to do programmatically? To say, because a lot of people would say, you know what? You actually slowed yourself down. We did two functions. Each of them wound up having to do this ranging process over all the symbols. And you could have done this a lot faster, Philip, if you just did all this in one go. Just write one for loop, and as you go, go backward through the string, and as you go, take the complementary nucleotide and append that to the list or the string that you're forming. And then that you'd only need one pass over the string. So that's definitely a more efficient way of writing the function. But most programmers would tell you that this is the better way of writing the function. And so my question for you is, why do you think that is? Why is this a preferable way of writing the function? And it's not because it's a one-line function, because notice we wound up with a bunch of additional code because we had to write two separate functions here. So why is it that this way of writing it is just objectively better? Give me some thoughts. I see some good thoughts already. Keep them coming. Readability from Javier and BZ already. This just looks right. There's something about this that's soothing to the eye. I want to reverse complement a DNA string, so I'm going to complement the DNA string. Then I'm going to reverse the result. It kind of makes sense. There's a certain elegance about it. That's true, and it's easy to read. Another point from a couple folks, Nada also said this, the two functions that we wrote now are reusable. We can apply these in additional contexts. So complement, not the most reusable function because this doesn't really serve a biological purpose that I can think of. I'm sure there is one. But reverse is the type of function, absolutely. And it's close to something that's built in Python. But I think you get my point that in general, this could be doing something more complex. And now because we've written these two functions, we can reuse each of these individual functions if the context arises for us to need them. There's one other point, though, Yeah, and I see it from AB. It's certainly clearer. But there's the notion of making a mistake, right? And this, as you code more, what you're going to see is mistakes are just, bugs are just a way of life when you program. And if I've split my task up into two separate functions, reverse and complement, well, I want you to imagine, say I did something wrong. I was trying to be very clever, and I tried to write one function, reverse complement. I was like, I know how to do this. And then I noticed, oh no, the string isn't the appropriate length, or it's producing the wrong output. Whatever is going wrong here, I now have to debug reverse complement. Now imagine then, though, that I do it in this way, where I get a bug. And now I say, well, what I would do is I would check reverse of a collection of strings and test that function. And then I could check complement and I would test that function too. And you have like two independent functions now that you can test separately from each other. And you'll know, well, here is reverse. Maybe reverse is working. And we have confidence that it's passing a bunch of tests, but complement isn't. So what that's allowed you to do is you've separated out where the bugs are. And so in practice, what we'll often do is we want to use subroutines as often as we possibly can and reduce what our tasks are to as simple tasks as possible. Because if you have a function like reverse or complement that's doing what might seem like a very straightforward task, that's good because it also means that that function is something that is testable. So small functions are great. Delegation and laziness in computer science is a virtue and not a sin. And we're going to see that as we go. This is about as simple an example of that as I can show you because it's also practical. But we're going to see this exact sort of paradigm of writing as many functions as I can, subroutines being good, and organizing our code. This is going to come up throughout the course. So get comfortable with this. You're going to see this sort of thing as we go. Because what we're ultimately doing is having this critical focus on modularity, the notion that each component in a program is only doing one very specific thing. Because when you write code like that, it makes it easy to test, easy to debug, and you're going to be confident in its output. Plus, it's more readable. So it's a win-win-win situation. For now, I want to say a little bit more about substrings. So we've said something about, we've introduced strings. I want to be able to manipulate strings in different ways. And one of the ways I would obviously want to study them, there's clear biological context for this, is I want to study the substrings of that string, meaning what are the individual words that live within it. This is going to get at our ongoing theme of finding hidden messages within genomes. And to get at this, I'm going to create a folder, not inside of strings, but inside of SRC called Substrings. And let's say a little bit about this. And I'm going to just copy over some starter code for myself. And I'm going to say substrings. And there's also a little bit about sublists in Python that we're going to do. And I'm going to have my special 2 lines to say run main. Now, if we want to access a substring of a string in Python, Python uses a special notation. It's called text of I to I plus k to indicate the substring of text that starts at position I and goes up to, but not including. So just like with ranging, the same idea applies for substrings, the final position I plus k. So this will include the symbol at position I. It won't include the symbol at position I plus k. And this is often, for people who see this for the first time, it can seem confusing. Why on earth would we do this? The more you do it, the more natural it becomes. And it's, I think, the absolute best way of thinking about this, and one of the reasons, is that it gives you a convenience. So if I want to say, how long is this substring? All I have to do is subtract this minus this. So subtract the top index minus the bottom index to give the length. Okay, so the string above has length k. Why? Because I plus k minus I is equal to k. So in general, you just subtract the two indices and that will tell you how long the substring is. That's nice. So I'll go back and I'll say, let's go back to our hi lovers string. Oh, okay, sorry. And then we're going to say, let's print s of 1 to 5. And so we know that the string is 0 indexed because it's a tuple, and everything, tuples and lists in Python are 0 indexed. So we're not going to pick up the h, but we are going to pick up the I. And then I could count out, okay, I go up to, but not including position 5. But using this convenience, I want you to think, oh, it starts at position 1, and it has length 4. Why? Because 5 minus 1 is 4. Okay, so when I save this, let me go to my terminal and cd up a directory and then cd down into substrings. I can say python 3 main.py, or Python if you're on Windows, and run it. And you're going to have I space LO. So that's where we know that this has length 4. And it is I space LO. We can print some other substrings. So let's get in the habit of this. Let's print a prefix, meaning a substring that's at the start of the string. And if I wanted to print, I don't know, s of 0 to 7. So this starts at position 0, it has length 7, and that's just going to give us, oh, that's going to be nice. It's going to be hi love. I could print it in that way, or I could say, well, I also know if I want to print a suffix, that suffix needs to end at position length of s minus 1. So if I wanted to print s of 4 colon, it's so tempting to say, oh, I know that the symbols go up to and including length of s minus 1. But remember, this position is not included. Okay, so we don't include the symbol at position 5 here. We don't include the symbol at position 7 here. And so if we want to include that final symbol of s, we need to make that length of s and not length of s minus 1. Another thing that's actually kind of a nice convenience here, because I still get to use length of s. If I want to go up to the end of s, I just put length of s there because it's not going to include that symbol. Okay, and this is going to be, what is this going to be? This will be everything starting at position 4. And so position 4 of the string is 0, 1, 2, 3, 4. So O, and that's just going to be overs. So when I save this and I hit up to run it, I'll see that this says hi love, this says overs. And I'm showing you prefixes and suffixes because there's a nice little shorthand thing that we can do, which is to say, I don't need to specify that first 0 here. And I don't technically need to specify this final element. So that will say, just take me to the end of the string. So I'll say this is or s of 0 to 7. And this is or s of 4 to the length of s. In practice, you don't even have to write length of s. And this is really nice. But I want you to know that in the background, that's what's happening. The same sort of notation that applies to substrings applies to lists as well. So, for example, I want you to imagine that I declare a list A, and I set A to be equal to, I don't know, a bunch of zeros. So it's a list containing 6 zeros. Let's give it some values. So what I'm going to say is let's range over the length of A. And I'm going to set A of I is equal to 2 times I plus 1. Okay, so that's going to ensure you can go through and say, what is this going to be? The first element is going to be 2 times 0 plus 1, so 1, and then 2 times 1 plus 1, so 3. And so at the end of this, you know, A is going to be now 1, 3, 5, 7, 9, 11. The first 6 prime numbers. And these are just all odd numbers. And I'm just giving you some values in A so you can understand what we're working with. So we can print A, and I'll show you. 1, 3, 5, 7, 9, 11. And then we can also print some sublists. So if we're looking for contiguous sequences of elements within the list, and I wanted to, I don't know, grab the one that starts at position 3 and has 2 elements in it, well, I could say, yeah, I know it starts at position 3. If it's got 2 elements, the top index minus the bottom index should be equal to 2. So I'm going to print A of 3 to 5. You see how easy that is? Same thing, if I want to find the first 3 elements of the list, well, I would start at 0 and then go up to 3. And I can leave that out. So we know that this is the prefix list of length 3. And I could also print everything starting at element 4 up to the end. And I can run all of that, and you'll see, well, here's the first thing that we printed, A of 3 to 5. That's 7 and 9, so it has length 2, starting at position 3. Then we print the sublist of length 3 that starts off the list, and that's 1, 3, 5, which we see there. And then we print everything starting at position 4 to the end. And that's A to 4, which is 9, 11, which is what we see there. Okay. Now, let me give you an exercise. As an exercise, and this is another one, I know you can do it. So I'll let you do that. The function I care about is, let's call it pattern count. And it's going to take a pattern as a string. And it's going to take a text as a string. And it's going to return an integer. And I keep generating these things. The way this function works is it's going to find the number of times that pattern, I should say a pattern, occurs in a longer text string. So if we look at parameters, we're going to have pattern as a string, and we're going to have text as a string, the longer string. And then it's going to return, well, in this particular case, it's an integer, and it's the number of times that pattern occurs in text, critically, with overlaps. So we should specify this. And what I mean by that is, ATA occurs twice in ATA. It occurs here, and there's an overlapping occurrence of it in the final 3 symbols. So I'm going to count that as an overlapping occurrence and say, I want the function to return 2. Now, as I said, you know enough to do this. I'm going to hand over the power to you. Write this function, and then we're going to discuss. Give you another minute or so. The first thing we probably should do before we even plan out code is to say, well, what are the possible bad outcomes in terms of parameters that we could plug into this function? So one thing we could say is, well, let's make things as clear as possible. I'm going to set k equal to the length of the pattern, and I'm going to set n equal to the length of the text string that I care about. And something that would be really bad would be if k is less than or equal to 0, right? Well, I suppose we're assuming that a string is being given, but if k were equal to 0, well, then we could say raise as a value error, empty pattern not allowed. Okay, so if you tried to give this an empty string, that would be a problem. Another case that you might check would be, well, what if the pattern was longer than the text? So if k is bigger than n, that would be bad. And you could imagine that maybe we raise a value error in that case too, but it might make just more sense to return 0 in that case. Once we've done some of this parameter checking, then we should say, let count, some variable that we're going to work with, equal to 0. And way down here, that's what I'm going to return. So I think about what's the variable that's going to store the answer. I'm going to call it count. Certainly it needs to start at 0. And then the idea that we're going to have is, well, range over the text. And we're going to increment the count variable every time we find a pattern match. So I know how to range over a text. I can say for I in range of n. And then I'm going to say, does the current substring of text of length k match my pattern? And we can check if two strings are equal. So just like checking if two integer values are equal, we can use the double equals symbol. So I can say, is it the case that the pattern that's my input, does it match the current substring of text? And here's where the new part is, right? Everything else here should be comfortable. It's what we've been doing. Then we say, well, what's the current text of length k? And here's where I said, well, I want, if I'm looking for a substring of length k that starts at position I, that's how I introduced this code along. So we said, that's the substring of text starting at position I of length k. Well, for it to have length k, the top index, the second index, needs to be I plus k, because when you subtract these two things, you wind up with k. If that's the case, what do I want to do? Add 1 to count, because I found a match. You might never find any matches. You might find a bunch. Every time you see this, I'm adding 1 to count. And then we're going to return count at the end. I could test this on a simple hypothetical pattern and text in main. So for example, I'll give you the example that we had before. Maybe pattern is ATA, and maybe the text is, I don't know why I'm putting text in quotes, text is equal to ATA. And what we want to print is the pattern count of these two things. And it's important to notice, here's one way your function could get out of control. I don't know about out of control, but here's one way you could make a mistake. Let's make pattern the first parameter and text the second one. If you get these backwards, what's going to happen is you're just going to have 0 because your input pattern would be longer than the text. But pattern comes first and then text. And when you print this, hopefully, we should see what we said we should see, which is 2. So I wanted to print 2 when we call this. My question for you is that what's going to get printed? What do you think? Yes? If no, what do you think might happen? Am I tricking you? Could I be? It's not happened before. Let's look at pattern count. BZ says out of bounds. Let's see what happens. We get 2. All right, we get 2. So the correct answer is being obtained by the function. I don't know if this is a good thing because function is not good. Like, it's given us the right answer and it's going to give us the right answer forever. And I get 2, and we can give it some more inputs. But I want you to see what's happening here, which is I want to print the current pattern. The current pattern is text of I to I plus k. And what you would hope is you're going to see all the k-mer substrings of the input text. So I'll say the current substring is, okay, and then we're going to print it. So that means you want to see the first one was the example I had, ATA, and then you're going to see TAT, and then you're going to see ATA, right? Except that what happens when you print this is you see a bunch of other stuff. You see TA and A. So you see ATA, TAT, ATA, but then you see TA and A. So then, yeah, what is going on? We're dealing with the fact that my ranging is wrong. So I has ranged all the way up to the final element. And so I want you, in this particular case, this is ranging what? N is 8, if our string is ATA, N is equal to 5. So the range is happening from 0 to 4 inclusively. And that means like when I is equal to 4, and we look at our string, it's trying to take the string starting at position 4 of length 3. There is no such thing. In a lot of languages, in this particular case, would say error, right? And Python doesn't. And it's kind of similar to what we saw before when we looked at like negative indexing and Python just kind of being okay with something, but then it being okay with something leads you down to another corridor where probably an error should happen, but because it's tried to give you this nice feature, it's not giving you an error. It produced an output that in the case we saw before was actually dangerous because it was obviously wrong. And yet it seemed like we had solved the problem correctly. This is another case where we've written the function incorrectly and it's like kind of okay because it's going to still solve it. But you can imagine we're eventually going to get to a point where we can't just keep writing code that's wrong and expect to get away with it. So this is a case where probably this should not be allowed. I'm trying to rack my brain for a reason why you would want to allow the indexing of a string to go beyond the string. But Python's like, that's okay. You said so we went beyond the string. That's all right. I'll just truncate what you want. And it's no big deal. I don't know if that makes a lot of sense, but what we should do is make sure that the function actually is correct. And the idea here is we have another pattern, right? We know we don't want to go all the way up to n. Where is it that it should go to? What is our pattern in this case? if it doesn't go all the way up to n. One good idea, I actually like this, was somebody gave us a specific example, like a specific number. And in this case, like, well, we would want I to start with 0, go up to 1, also include position 2, but it shouldn't have position 3. So it should go from 0 to 3. Right? And then the question is, yeah, how do we take that idea of this specific example and say, what should it go to in general? It's not going up to 5. I see some good answers in the chat. It is very tempting to just say, oh, it's n minus k, because we're going to miss out those final elements. But be careful about this, because in the case we saw before, what's n minus k for this example that we have? 5 minus 3, which is 2. So we would go position 0, position 1, and if I range up to 2, we're not going to include position 2. So this would be just slightly off. I'll actually show you, because I'm going to print the current substring. If we take it up to n minus k, and then I run the code again, we're going to get ATA, we're going to get TAT, but we're not going to get that final ATA. So when we print the current substrings, we see that we're missing one, and we're going to be 1 short. So I'm going to add a 1 there to make everything okay. I saw some good answers in the chat. I couldn't fool you. You're getting really good. All right, n minus k plus 1. And we see that we're capturing all the substrings in this case. And we probably should test this on a bunch of other inputs, but this is the correct formula. It actually indicates something that all computational biologists probably should know, which is that there are n minus k plus 1 total substrings of length k in a string of length n. Okay, and they range from position 0 to n minus k. I should say starting position. All right, and now we've got a functional function. I could, let's see, that's good. I'm going to remove this print statement too. Oop, went a little bit too far there. Now, I would contrast this just to show you something. I also would point out, some people might say, we have a built-in function to do this. There actually is a function that I can call just text dot count of pattern. So that's built into Python. And I want to point out what happens, which is that when I run this, it doesn't give us 2. So is this function wrong? Did it miss one? And the answer is no. The answer is this just doesn't include overlaps. So I wanted to include this to show you. Here is probably our first example of something that is like much of what we do in the start of the course. There's often a Python equivalent for what we're doing that is built in. But we're showing you some of the types of tasks that are fundamental. And so we're not just going to always use these built-in things. Here's an example of a built-in function that produces a result that doesn't match what we would want in the case of something like computational biology. So if you're looking, for example, for a motif or a protein DNA binding region in DNA, something that the protein is binding to, you probably want to count, you probably want to consider overlapping occurrences, because each possible overlapping occurrence is one way, one opportunity for the protein to bind there. And so you'd want to count these. But here's an example of the standard built-in counting in the language that doesn't match that. So even though it's not a very complex task, it's still differing from what we get when we look at what's built in. So it's never a bad idea, in other words, to solve problems yourself. All right, let me ask you, now that we can do this, I'm going to show you one other function. And that function is going to be called, let me pull this down for a second. This function is going to be called starting indices. So I'm like, you know what? I can count the number of patterns number of times that a pattern occurs in a text. But there's a related question that I think is more general, which is maybe I could find where it is that this pattern occurs in text. And I'm not going to return an integer. What I'm going to return in this particular case is a list of integers. And I'm going to reuse my docstring here, so just so I don't have to do a bunch of typing. And in this case, I'm going to say, I'm not finding the number of times that a pattern occurs in a longer text string. I'm going to find all the occurrences where this happens. I'm still going to take a pattern and a text, so 2 strings. And then instead of an integer, I'm going to return a list of integers. And what I'm returning is the collection of starting positions where the pattern occurs in the text. And we want to consider overlaps as well. Okay, so ATA occurs at positions 0 and 2 in ATA, TA. And I could write this function, and I think this is not a big leap from what we've done. Instead of starting off, and really what I'm going to do is have the same checks. I still want to make sure that k is not equal to 0. I still want to make sure that I'm not trying to give a longer pattern than I am text. So I'm going to copy all that over. But then what I'm going to do is, well, I'm not counting the positions or the number of occurrences. I'm going to keep track of the positions themselves. So I'm going to return the positions at the end after I create this empty list. And then I want to still range over all the starting positions. And if I find a match, append it to positions. So I still am going to have a for loop. I'm going to range over everything from 0 up to n minus k plus 1, but not including n minus k plus 1. And then I'm going to say, if it's the case that text of I to I plus k is equal to my pattern, well, let's append it. So I'm going to say positions.append this position that I care about. So this tells me not just how many times they occur, but the specific occurrences where this pattern appears as a substring. Is this familiar? As I'm typing this out, right, I should be thinking something. And that something is, this feels so similar to what I've just done. Now, yes, I'm returning a different object. I'm returning a collection of starting positions instead of an integer, counting the number of things. But if you look at the code here, our checks are the same. And really the code here is kind of the same too, right? I'm ranging over all the possible substrings of length k. If I find a match, I'm adding one to this count. So instead of adding one to the count, I'm just appending that position that I found to this list of positions. And what have I said? What have I said about this? Whenever you start having this familiar feeling, what should this lead us to do when we're programming, right? Whenever I get deja vu and think I've typed this before, this is so similar to what I've just done. There's only like 10 words that you ultimately have to say in the class. A lot of times there's one-word answers. And you're going to see immutable is one that's very prevalent. And everybody else is now saying the other magic word, which is subroutine. So just as a rule of thumb, if you ever find yourself typing out the same code, what we've seen is that a good habit for programming is to think, well, maybe I can just use that code I've already written. And in this particular case, we've written a function that is actually more general than what we just did. So we've solved the general problem. And if we've solved this more general problem where, like, for example, if I tell you that a string occurs in a longer string 10 times, well, that doesn't tell you where to find them. But if I tell you exactly where to find them, you should be able to count the number of occurrences very quickly. In particular, like imagine, I probably should go up into main, and I should print the starting indices of this particular example that I have of pattern and text. And so we know where those are. They're at positions 0 and 2. That's where ATA occurs in ATA-TA. So if I print this out and I run it, I should see those starting positions, 0 and 2. But I can quickly solve the problem that I had before, which is counting the number of occurrences of pattern and text, if I just say, well, how many things are in there? So now that I've solved this more general question, I can get rid of everything that we've done with pattern count. And I mean, I guess I could leave in these tests as long as I am sure that these tests are being performed by the other function. I could take them out as well, but I'm going to keep them in, and I'm going to get rid of all the code that I just wrote in pattern count, and I'm just going to return the length of what happens when I call starting indices of pattern and text. And we have a one-line function. So I can run this and verify. Hopefully we're going to see this 2 here is going to stay. And we see that's the case. So nothing ultimately has changed. If I just say how many things are in that collection of starting indices that I returned, well, I can get that number of things just by saying it's a list, and I'm going to take its length. So the lessons learned here are anytime you see code that's repeated, number 1, there's probably a subroutine lurking. And there's another lesson too, which is that just like we saw with the greatest common divisor, there was an example where in order to figure out why is this Euclid's formula correct, this notion that GCD of AB is equal to the GCD of A minus B, or B A minus B if A is bigger. Why is that formula correct? And we went on this argument that said, well, instead of saying that the GCD is equal in that particular case, we could say the set of all divisors of these two numbers is the same as the set of all divisors of these two numbers. And so then the biggest one would obviously have to be the same too. That was a very brilliant initial argument from over 2,000 years ago, but it was an instance of sometimes you can solve a more general question and it doesn't necessarily make your work any harder. And sometimes it can make it easier. And in this particular case, we can solve the more general question of finding all the positions. And once I've solved that more general question, the initial question we looked at, which is actually counting them, becomes trivial. We just say, you've got a list. What's its length? That's, I think, it for now. We are comfortable now, I hope, with strings, which we know are immutable, magic word, because we're thinking of them as tuples of symbols. And we've also gotten some comfort here in working with substrings and sublists and going through and ranging through a string and starting to work with its substring structure. This is all going to be very powerful. We're going to look at a fundamental biological application next time, which is to catalog all of the substrings of a certain length within a longer string. And then we're going to say what occurs frequently. What is interesting about the substrings that we observe? This is one of the most important questions that we can do in biological data analysis. And I'm excited to do it, but you're going to have to join me next time for that. In the meantime, happy coding, and thank you for joining me.